Hey everyone, and welcome to this explainer. Today, we're going on the ultimate cosmic detective journey. We're going to uncover the origins of our universe, tracing everything we see today all the way back to the absolute beginning of time. And we're going to do it using only the hard scientific evidence presented in our sources. It's a fascinating story of intense heat, massive expansion, and truly unimaginable scales.
Okay, let's dive into this. 13.8 billion years, or, well, to be perfectly precise, an estimated 13.787 billion years. That staggering number is the age of our universe. That's exactly how long it's been since everything you know, everything you've ever seen, and everything that has ever existed was set into motion. But what exactly was that motion?
And that brings us to the Big Bang. It's the physical theory describing how the universe expanded from an initial state of extreme density and temperature. Basically, what started as a microscopic, intensely hot singularity gave birth to everything we know. Now, it's actually kind of funny when you look at the history here. The term Big Bang wasn't even created by the theory's supporters. It was coined during a 1949 BBC radio broadcast by astronomer Fred Hoyle, a rival scientist who favored a completely different theory. He actually meant it as a striking, slightly pejorative insult to mock the idea of a single explosive origin. But hey, the name stuck.
So here's our roadmap to reverse engineer the universe. 1. The expanding universe. 2. The cosmic timeline. 3. From atoms to galaxies. 4. Evidence of the Bang. And 5. Unsolved cosmic mysteries. Let's just jump right in.
Number 1. The expanding universe. Tracing the cosmos backward.
Before we can look at the very beginning, we really need to understand how humanity first realized the universe wasn't just sitting still in the dark. Back in the 1920s and 30s, pretty much every major cosmologist preferred what's known as the steady-state model. They believed the universe was static, eternal, and roughly the same at any point in time. It had no beginning and no end. But in 1931, a physicist and Roman Catholic priest named Georges Lemaire proposed this radical alternative. He suggested that the universe emerged from a single primeval atom and has been constantly expanding ever since.
The Moitre's proposition was incredibly profound. As he wrote, if the world has begun with a single quantum, the notions of space and time would altogether fail to have any meaning at the beginning. This was a massive paradigm shift, right? The Big Bang wasn't an explosion of matter into an already existing empty space. It was the explosion of space and time itself. Before the Big Bang, there literally was no where and there was no when.
And the ultimate smoking gun for Lemaitre's radical theory? That came from American astronomer Edwin Hubble. In 1929, using the massive Hooker telescope at Mount Wilson Observatory, Hubble observed that distant galaxies were actively moving away from Earth. More importantly, they were accelerating proportionally with their distance, a relationship we now know as Hubble's law. This absolutely proved the universe was expanding. And logically, if things are moving apart today, it means that a very, very long time ago, they must have been packed tightly together. Cosmology was changed forever.
Number 2. The cosmic timeline, the first fractions of a second.
Now, what's really interesting about this is the dizzying physics of the very early universe, where conditions were so extreme that even our basic concepts of particles just completely break down. Let's look at the absolute chaos of these unimaginably brief first moments. At 10 to the negative 43 seconds, we have the Planck epoch. Temperatures are at 10 to the 32 degrees Celsius. The entire universe is a fraction of a millimeter across, and all four fundamental forces of nature are crushed together into one. Then, at 10 to the negative 37 seconds, boom, cosmic inflation. The universe grows exponentially, driven by microscopic quantum fluctuations and completely unconstrained by the speed of light. By 10 to the negative 36 seconds, the electroweak epoch begins, and the strong nuclear force breaks away. All of this happening in way less than a blink of an eye.
Amidst all this violent, relativistic expansion, something incredibly lucky happened. An unknown reaction called baryogenesis occurred. In this boiling soup of extreme energy, matter and antimatter were constantly being created and destroyed in pairs. But baryogenesis caused a microscopic anomaly, a tiny imbalance leaving just one extra matter particle for every 30 million antimatter particles. A massive annihilation immediately followed, completely wiping out the antimatter. But that tiny leftover fraction of regular matter survived. And miraculously, that tiny fraction is exactly what makes up you, me, the planets, the stars, and absolutely everything we can see today.
Number 3. From atoms to galaxies, the great cosmic cooling.
So, after that blistering, chaotic fraction of a second, the universe began a long, dark, and super essential period of cooling. Let's walk through this process. As the universe expanded, the temperature finally dropped. In step 1, quarks and gluons could finally combine to form the very first protons and neutrons. In step 2, just a few minutes into the expansion, these protons and neutrons merge to form the first atomic nuclei, mostly hydrogen and helium, in a process called Big Bang nucleosynthesis. But it wasn't until step 3, roughly 380,000 years later, that things finally cooled enough for electrons to actually attach to these nuclei, forming neutral hydrogen atoms. This moment, called recombination, is profound. The universe completely transformed from a searing, opaque plasma into a transparent expanse, allowing light to finally travel freely through space.
And with that transparent space, the cosmic dark ages began. Slowly but surely, gravity went to work. It pulled those early, slightly denser clouds of hydrogen and helium gas together. It crushed them down until the immense pressure and heat ignited the very first stars. Over billions of years, these stars clustered together to form massive galaxies, which then crashed and combined to form the luminous, complex structures we recognize in our night sky today.
Number 4. Evidence of the Bang. How we know it happened.
So, the crucial point is, how do we actually know all of this happened? I mean, this isn't just guesswork, it's backed by hard science. Cosmologists rely on what are known as the 4 pillars of Big Bang evidence, essentially the ultimate cosmic fingerprints left behind by the event. First, as we discussed, Hubble's law proves the continuous expansion of the cosmos. Second is the cosmic microwave background radiation. Third, the highly specific, predicted abundance of primordial light elements like hydrogen and helium perfectly matches our observations. And fourth, the observable evolution and distribution of galaxies over massive scales of time perfectly aligns with a universe that started small and grew over billions of years.
I want to focus on that second pillar for just a moment. Discovered entirely by accident in 1964, the cosmic microwave background, or CMB, is the uniform, leftover radiation from when the universe first became transparent 380,000 years after the Big Bang. It's essentially an echo of that initial cooling phase. And to connect this directly to you, this ancient fading heat from the birth of the universe is actually a tiny fraction of the static you would see on an old, untuned television set. You can literally observe the aftermath of the Big Bang right in your living room.
And finally, number 5, unsolved cosmic mysteries. What we still don't know. Now, while the Big Bang model is widely accepted and incredibly accurate, we are definitely still pushing the boundaries of our understanding, looking out into a universe that still holds some pretty profound secrets. And the scale of those secrets is staggering, and this brilliantly illustrates it. Consider the current mass energy density of the universe. All of the normal matter, every star, every planet, every comet, you, me, everything we have ever interacted with, makes up a measly 5% of the universe. The rest, it is completely invisible to us. 27% is dark matter, an unknown substance that helps bind galaxies together. And a whopping 68% is dark energy.
So what exactly is dark energy? Well, it's this mysterious force that is causing the universe's expansion not just to continue, but to accelerate. It's pushing galaxies apart faster and faster. And because of this dark energy, there is a literal future horizon. Eventually, distant galaxies will be receding from us so fast, actually faster than the speed of light, that their light will never be able to reach us again. They will simply fade away into the cosmic dark.
Which leaves us with a pretty provocative cliffhanger. If dark energy continues to infinitely accelerate the expansion of the cosmos, pushing everything further and further apart, what is the ultimate fate of our universe? Will it stretch until everything simply freezes and fades away? The Big Bang tells us exactly how our cosmic story began, but the ending? Well, that is a mystery we're still trying to solve. Thank you so much for joining me on this explainer. Keep looking up, keep asking questions, and I'll catch you next time.